There is a planet glowing magenta somewhere beyond our solar system right now. There is another one made almost entirely of crystalline carbon, denser than any diamond on Earth. There is a world with a second atmosphere that it grew after its first one was destroyed. There is a planet we call red, but if you could stand on its surface, the sky above you would be pink. These are not science fiction. These are confirmed observations. And every single color, from the rust of Mars to the magenta of a newborn giant, to the pale cyan of a world twice the size of Earth, is a message, not a decoration, not an accident, a chemical signature, a temperature, a history. And once you learn to read it, nothing in the night sky will ever look quiet again. If this journey through the colors of worlds has given you something to carry tonight, the kindest thing you can do is like this video and subscribe so we can keep making these voyages together. Go ahead and find a comfortable position now. In 3, 2, 1, liftoff. Open any textbook. Find the page with the solar system laid out in a row. You have seen this image so many times it barely registers anymore. Mercury, gray and small. Venus, pale and bright. Earth, blue. Mars, red. Jupiter, striped in orange and cream. Saturn, ringed and yellow. Uranus, blue-green. Neptune, deep blue. You process those colors as a child, the same way you process the colors of a traffic light as signals, not as substance. Red means stop. Mars means red. Neptune means blue, and that was the end of it. But here is what nobody ever told you. Every single one of those colors is a scientific instrument. Every shade, every hue, every gradient between one tone and the next is a direct physical measurement of what a world is made of, what it has survived, what is happening inside it right now, and whether it is alive or dead. When you look at the color of a planet, you are not seeing decoration. You are reading a chemical signature written across hundreds of millions of square miles of atmosphere, or rock, or ice. You are receiving a message that has traveled across hundreds of millions of miles of empty space to reach your eye. And most of us have spent our entire lives looking at those messages without ever learning to read them. That changes tonight. We are going to move through the solar system and beyond it, and by the time we are done, you will never look at a planet photograph the same way again. Not because the colors will look different. They will look exactly the same. But what you will see inside them, the chemistry, the violence, the age, the temperature, the biology will be completely new. It is like learning that every shadow on a wall is actually a word in a language you never studied. The shadow does not change. Only your understanding of it does. And once you can read shadows, walls become books. Let us begin at the edge. Not the center of the solar system, not with the bright familiar blue of Earth, but with the closest world to the sun, a world that most people forget about entirely. Mercury is gray, not a dramatic gray, not a striking silver, not the gray of storm clouds building before lightning, just gray, the gray of old concrete, the gray of ash, the gray of a world that has given up every pretense of complexity and reduced itself to the bare minimum of what a rocky body can be. If you did not know it was a planet, if you saw a photograph of Mercury without a label, you might think you were looking at our moon. The resemblance is not coincidental. The explanation for both is the same. Mercury has almost no atmosphere. What it technically possesses is so thin and so fragile that scientists call it an exosphere rather than an atmosphere, a scattering of atoms so sparse that the particles almost never collide with each other. There is no weather on Mercury. There are no clouds to filter sunlight. There is no chemical soup in the sky to react with incoming radiation and produce compounds that would scatter certain wavelengths and absorb others. When sunlight hits Mercury, it hits bare rock, bare iron, bare nickel, bare silicate, and it bounces. What comes back to your eye is simply what was always there, the natural gray-brown color of iron, nickel, silicate minerals in their unprocessed state. There is nothing between you and the rock. No filter, no chemistry, just the raw material of a planet with nowhere to hide. In June 2024, the European Space Agency's Bepi-Colombo spacecraft flew past Mercury and returned images of extraordinary detail. The surface looked like it had been sandblasted for 4 billion years, which is exactly what has happened to it. Without an atmosphere, every meteorite and piece of cosmic debris that has ever crossed Mercury's path has hit the ground directly, carving craters that will last until the sun swells and swallows the planet whole. Mercury's gray is the gray of extreme exposure. It is the color of a world with no protection and no chemistry to speak of, stripped down to mineral and metal by the violence of formation and 4 billion years of solar bombardment. The contrast with the world immediately next door is so severe that it stops you in your tracks. Venus is not gray. From space, Venus looks like a pearl, or a lemon, or a lantern, a golden white brilliance that makes it the brightest object in the night sky after the moon. Ancient civilizations built calendars around it. Sailors navigated by it. Poets called it Hesperus, the evening star, and Phosphorus, the morning star, not realizing for centuries that it was the same object appearing at different times of day. Even today, when you see Venus hanging low on the horizon in the hour after sunset, it looks luminous, almost warm, almost welcoming. It looks like somewhere you might want to go. Do not go there. What you are seeing when you look at Venus is not a surface. The surface of Venus is hidden from every optical telescope that has ever been pointed at it, hidden beneath a cloud deck, so deep and so dense and so completely unbroken that no sunlight reaches the ground in any meaningful quantity. What you are seeing is the top of those clouds, and those clouds are made of sulfuric acid. The atmosphere of Venus is 96% carbon dioxide, with a surface pressure 92 times greater than Earth's. At sea level, approximately the same pressure you would experience if you were submerged 9 to 100 meters in the ocean. The temperatures at the surface reach 860 degrees Fahrenheit, hot enough to melt lead. But the color we see from space has almost nothing to do with the surface chemistry. The golden white color of Venus is the signature of its upper cloud layers, roughly 45 to 70 kilometers above the ground, where sulfuric acid droplets and ice crystals scatter sunlight with extraordinary efficiency. Sulfuric acid clouds are highly reflective. Venus reflects approximately 70% of all the sunlight that hits it, a reflectivity called albedo that is the highest of any planet in the solar system. This is why Venus appears so blindingly bright from Earth. All that reflected light has to go somewhere, and most of it goes back into space. But the precise wavelengths it reflects, and the slight yellowish golden tint that distinguishes Venus from a perfectly white mirror, come from trace amounts of an absorbing compound that scientists spent decades trying to identify. As recently as 2023, research continued pointing toward ferric chloride and other sulfur-based compounds as the agent responsible for absorbing ultraviolet light in the cloud tops, producing the subtle golden hue that human eyes perceive as warm and inviting. There is nothing warm about it. It is corrosive acid 3 times over, baking in a runaway greenhouse effect so severe that Venus serves as the most vivid warning in the entire solar system about what happens when a planet loses control of its own atmospheric chemistry. The golden glow of Venus is the color of a catastrophe that has been running for billions of years. It is beautiful the way a wildfire is beautiful from a distance, from safety, from a world that made different choices. And then there is Earth. From space, Earth is blue. That is the fact everyone knows, the fact almost nobody stops to examine. Why is Earth blue? The answer that most people would give, because it is covered in water, is true but incomplete. The oceans do absorb and reflect light in ways that contribute to Earth's blue appearance. But if you look at photographs of Earth from space, the blue you see is not simply the reflection of a flat blue mirror. It is luminous, layered, alive. Part of that comes from the oceans, but a significant part of the blue that fills Earth's atmosphere, the haze, the soft gradient from space, the color of the sky, as seen from any mountaintop on any continent, comes from a process called Rayleigh scattering. When sunlight enters Earth's atmosphere, it collides with the nitrogen and oxygen molecules that make up most of our air. These molecules are much smaller than the wavelengths of visible light. When light hits them, it scatters, but it does not scatter equally for all colors. Shorter wavelengths scatter more powerfully than longer ones. Blue light has a shorter wavelength than red or yellow or green light. So when sunlight hits our atmosphere, blue light scatters in every direction, forward, backward, sideways, upward, downward. No matter where you look in the sky when the sun is up, blue light is reaching your eye from every angle because the entire atmosphere is scattering it toward you from everywhere at once. The sky is blue because blue light is lost from its original path and redistributed across the entire dome of air above you. When astronauts look back at Earth from orbit, they are seeing this scattering from the outside. The thin blue halo of Earth's atmosphere that glows in every photograph taken from the International Space Station is the sum of all that scattered blue light. It is a color produced by the collision between sunlight and the chemistry of a nitrogen-oxygen atmosphere. On a planet with a different atmospheric composition, carbon dioxide like Mars, methane like Titan, sulfuric acid clouds like Venus, the sky would be a completely different color. The blue of Earth's daytime sky is a direct signature of the specific molecular composition of our air. If you could read it, you would know exactly what the atmosphere was made of without ever taking a sample. But that blue is only half of what Earth shows the universe. The other half is green, and green is a completely different story. When you look at a global map of Earth's land surfaces, roughly 30% of the land area, somewhere between 12 and 14% of the total Earth's surface, is covered in forest. If you add grasslands, wetlands, croplands, and all the other forms of vegetation, somewhere between 40 and 50% of Earth's land surface is covered in photosynthesizing organisms. These organisms contain chlorophyll. Chlorophyll is a molecule that absorbs red and blue light from sunlight and reflects green light back into space. This is why plants are green. This is why forests seen from satellite look emerald, why meadows glow in low-angle sunlight, why algae blooms in the ocean tint the water with a visible haze of living color. The green on Earth is not a geological feature. It is not the color of a rock or a gas or a mineral. It is the color of life itself, projected onto the surface of an entire planet by 400 million years of photosynthetic organisms, covering every available surface with their light-capturing machinery. When you look at the green in a photograph of Earth taken from space, you are seeing evidence of an entire planetary-scale biological engineering project that has been running continuously since the Devonian period. You are seeing the reflection of billions of tons of chlorophyll. You are seeing a biosphere announcing its presence in visible light. No other confirmed planet in the solar system shows this color signature. Not even close. Mars is red-brown. Venus is white-gold. The gas giants are striped in chemistry that has nothing to do with biology. The green of Earth is the rarest color in the solar system, not because green is chemically impossible on other worlds, but because producing a green planetary surface requires life to have been operating at a massive scale for an enormous duration. It requires organisms to have colonized continents, to have evolved efficient photosynthetic mechanisms, to have persisted through mass extinctions and ice ages and volcanic catastrophes, and to have come back every single time and covered the rock again with their green machinery. Earth is green because life is stubborn, and the color proves it from orbit. Now consider what we just moved through. 3 planets in a row: Mercury, Venus, Earth, each with a completely different color, each color produced by a completely different physical process. Mercury gray from the absence of atmosphere, Venus gold from the chemistry of sulfuric acid clouds, Earth blue from the molecular scattering of nitrogen and oxygen, and Earth green from the photosynthetic machinery of a living biosphere. We have not even reached Mars yet, and already the lesson is becoming clear. Color is chemistry. Color is process. Color is consequence. Mars is red. This is the most famous planetary color in astronomy, the nickname every child knows, the reason ancient Romans named the planet after their god of war. The red of Mars is iron oxide, rust, the same chemistry that turns a forgotten nail orange-brown over a winter left outside, the same reaction that stains concrete walls in abandoned buildings, the same compound that colors the blood-red bands in banded iron formations in Earth's oldest rocks. Iron plus oxygen plus time. That is Mars. But understanding why Mars is rust-colored requires understanding how it became that way, because the story is not as simple as a planet that was always rusty. Early Mars almost certainly had liquid water. The evidence is written into the geology in unmistakable ways. Ancient riverbeds carved into the bedrock, mineral deposits that form only in the presence of liquid water, dried lake beds, visible from orbit as perfectly flat, pale plains. Between 3 and 4 billion years ago, Mars may have had an ocean covering a significant fraction of its northern hemisphere. It may have had a thicker atmosphere. It may have had a magnetic field strong enough to protect it from solar wind stripping. Then Mars lost those things. The magnetic field weakened and eventually collapsed, possibly because the planet's smaller size meant its iron core cooled faster than Earth's and stopped generating the dynamo that produces a planetary magnetic field. Once the magnetic field fell, the solar wind, the constant stream of charged particles flowing outward from the sun, began stripping the upper atmosphere away, particle by particle, year by year, over hundreds of millions of years. As the atmosphere thinned, the pressure dropped. As the pressure dropped, liquid water could no longer remain liquid at the surface. It either boiled away, froze, or chemically bonded with the rocks. And in the process of all that chemical bonding, the iron-rich rocks of the Martian surface reacted with what little water and oxygen remained, and they rusted. The surface of Mars did not start out red. It became red through the chemical reaction of a dying world, a planet losing its water and its air and its future, staining itself with the byproduct of that loss. Every photograph of Mars's surface, every sweep of red dust across a plain, every red-tinged ridge of a crater wall is a record of that death. You are not seeing a color, you are reading an epitaph. But here is something that almost never makes it into the casual description of Mars's color. The ground is not the only thing that is red. The sky of Mars is not blue. On Earth, the nitrogen and oxygen in our thick atmosphere scatter blue light so effectively that the sky appears blue even when you look at it from the surface. On Mars, the atmosphere is too thin for effective Rayleigh scattering of blue light. The atmosphere is about 1% of Earth's surface pressure, a near vacuum by Earth's standards. But Mars's thin atmosphere is loaded with fine iron oxide dust suspended in it, essentially permanently. This dust does not absorb or reflect the same way atmospheric molecules do. Instead, it scatters and absorbs wavelengths in a way that makes the daytime Martian sky appear a muted, salmon pink or butterscotch color, depending on the amount of dust present. During global dust storms, the sky turns a darker rust orange. On a clear day by Martian standards, the sky is a pinkish tan that gradually brightens near the horizon. Martian sunsets are the reverse of Earth's. On Earth, sunsets are red and orange because those are the long wavelengths that survive when blue light is scattered away. On Mars, the blue light actually survives better near the sun during twilight because the thin atmosphere and the dust act together in a way that is almost the opposite of our own. Near the sun, Martian sunsets are often described as pale blue and blue-gray. Human eyes on the Martian surface would see a pink sky that turns subtly blue near the setting sun. Every single detail of that sky, the pink, the dust, the inverted sunset colors, is the direct consequence of iron oxide. One molecule, one element, and one compound repeated across an entire planet's atmosphere and surface for billions of years, painting everything the same, terrible color. Now we leave the rocky inner planets and move outward, past the asteroid belt, into the realm of the giants, and the color story gets more complex, more layered, and ultimately more mysterious. Jupiter is the largest planet in the solar system. It is also the most visually spectacular. Every photograph of Jupiter is a display of fluid dynamics and atmospheric chemistry operating at a scale that should be physically impossible. The planet is wrapped in alternating bands of color, light zones, and dark belts stretching parallel to its equator, dozens of them stacked from pole to pole, each one a different shade of white, cream, yellow, orange, brown, or red. Superimposed on these bands are ovals and vortexes and spiral storms, some of them larger than entire planets. The most famous is the Great Red Spot, a storm that has been running continuously for at least 350 years by current estimates, a hurricane larger than Earth that has persisted through the entire modern era of human civilization without ever once stopping. What produces all of this color? The underlying atmosphere of Jupiter is hydrogen and helium, both of which are completely colorless. If you could somehow separate out all the other compounds in Jupiter's atmosphere and compress them into a pure hydrogen-helium mixture, the planet would appear white or pale gray. All of the color comes from trace compounds, and the identity of the most important of those compounds is still not fully resolved. In the upper atmosphere, where the temperatures are cold enough around -220 degrees Fahrenheit, and below ammonia gas freezes into tiny white ice crystals and forms the highest cloud layer. These clouds are white in their pure state. They form the light-colored zones in Jupiter's banding. But the zones are not purely white. They carry tints of yellow and cream, and the dark belts, which sit lower in the atmosphere, where temperatures are warmer and ammonia clouds cannot form, are not simply darker, but genuinely colored in orange, brown, and reddish-brown. The coloring agents, the chromophores, as scientists call them, are the great unsolved mystery of Jupiter's palette. For decades, researchers proposed that sulfur compounds were responsible, since sulfur produces vivid yellow and brown tints. Others pointed to phosphine gas, which can be converted by ultraviolet radiation into red phosphorus compounds near the cloud tops. Laboratory experiments in which ammonia and acetylene are exposed to ultraviolet radiation produce reddish organic compounds called tholins, which have been proposed as candidates. None of these explanations has been definitively confirmed by direct measurement from within the Jovian atmosphere. The chromophores of Jupiter remain, as of this writing, a partially open question. What is confirmed is that the banding structure itself is the product of Jupiter's powerful wind systems. Jupiter rotates faster than any other planet in the solar system, one full rotation in just under 10 hours, despite being over 11 times the diameter of Earth. This rapid rotation stretches atmospheric circulation into the east-west bands that we see. The light zones are regions of rising gas, cooler and higher. The dark belts are regions of sinking gas, warmer and lower. The different altitudes expose different cloud layers and different chemistry to sunlight, which is why the zones and belts appear different colors. The entire banded structure you see in a photograph of Jupiter is a map of its atmospheric circulation, colored by chemistry. The Great Red Spot is a special case. It is an anticyclone, a high-pressure storm system that has been stable for centuries. Its red color is still debated, but the leading hypothesis involves the storm lifting ammonia ice up to extremely high altitudes, where ultraviolet radiation breaks it down into compounds that produce a reddish-orange tint. The color of the Great Red Spot has actually changed noticeably over the last several decades. It was a deeper brick red in the 19th and early 20th centuries, and has faded to a more salmon orange in recent observations, possibly because the storm has been weakening and its updrafts are no longer as powerful. Even the color of an individual storm is a real-time readout of the dynamics within it. Saturn has often been described as a quieter, calmer version of Jupiter, and in terms of banding structure, that is broadly accurate. Saturn's atmospheric features are more muted, the bands less vivid, the storms rarer and less dramatic. But Saturn's color is distinct. Where Jupiter has a palette that runs from white through yellow to deep orange and brown, Saturn has a more uniform appearance, a hazy, warm yellow-beige that covers most of the visible disk, interrupted by occasional pale brown bands and rare white storms. The mechanism behind Saturn's yellow color begins in the same place as Jupiter's with ammonia. Saturn's atmosphere is also primarily hydrogen and helium, with trace amounts of other compounds including ammonia, methane, ethane, acetylene, phosphine, and water vapor. In the upper atmosphere, ammonia freezes into clouds of white ice crystals. Pure ammonia ice should be white, as it is on Jupiter's highest cloud layer. But Saturn's cloud deck is topped with a thicker, deeper haze layer than Jupiter's. Saturn is colder than Jupiter. Its cloud tops sit at around -270 degrees Fahrenheit, and its lower gravity allows clouds to form at greater altitudes and spread more diffusely. This thicker haze creates a kind of veil over the underlying cloud structure, softening the contrast between zones and belts and giving the planet its more uniform, muted appearance. The yellow-beige color itself comes from photochemical reactions happening within and above the cloud deck. When ultraviolet radiation from the sun hits the ammonia, phosphine, and other gases in Saturn's upper atmosphere, it drives chemical reactions that produce complex, organic and inorganic compounds, the chromophores. Phosphorus-containing molecules are among the primary candidates, as they produce yellow and orange tints. Sulfur compounds are also implicated. These compounds do not remain in the upper atmosphere. They are constantly being produced by solar radiation and then rained down onto the cloud tops below, staining the white ammonia ice crystals into the amber and yellow hues that cover the planet's visible face. Saturn's rings, which are so enormous and so geometrically precise that they look like they should be artificial, add another layer to the color picture. The main rings are composed almost entirely of water ice fragments, ranging from dust grain-sized particles to chunks the size of houses, all of them orbiting Saturn in a disk that is nearly 300,000 kilometers wide, but on average only about 10 meters thick. Pure water ice appears white, and Saturn's rings do appear bright and white in many images. But the rings also contain trace amounts of rocky silicates and organic compounds that give different regions slightly different tints, some slightly red, some slightly gray. The color variation in the rings is itself a map of their composition and their history of collisions and contamination. In 2025, new research published in the Journal of Geophysical Research using observations from multiple telescopes further refined our understanding of the ammonia distribution in both Jupiter and Saturn, confirming that the primary coloring agents in both planets are produced photochemically near the cloud tops rather than being intrinsic properties of the deeper atmosphere. The color is a surface phenomenon in the atmospheric sense, produced where sunlight meets chemistry at the highest altitudes. Deeper in both planets, beneath the cloud layers, the temperatures and pressures climb so rapidly that the concept of color in the conventional sense ceases to apply. At a certain depth, there is no more sunlight to reflect. The color of a gas giant is the color of its skin, its outermost shell of chemistry exposed to starlight. Something happens at an even greater depth that almost nobody mentions when they talk about these planets' colors, and it is one of the most remarkable things in the solar system. Deep inside both Jupiter and Saturn, hydrogen, which is a gas at the pressures we experience on Earth's surface, is compressed to such extreme densities that it transitions into a liquid and then into a metallic state in which electrons flow freely through the hydrogen just as they do through a copper wire. This metallic hydrogen is the source of Jupiter's powerful magnetic field. It conducts electricity on a planetary scale and rotates with the planet, generating a magnetic field 14 times stronger than Earth's. You cannot see this from outside. The beautiful colored bands you see in a photograph of Jupiter are the ceiling of a world that becomes incomprehensible before you have even reached its center. Saturn, as it turns out, is stranger still in one specific way. Saturn is the only planet in the solar system less dense than water. Its average density is approximately 700 kilograms per cubic meter, compared to water's 1 to 1,000 kilograms per cubic meter. If you could find a bathtub large enough, and the image is absurd, but it is scientifically accurate, Saturn would float. Its enormous size and relatively low mass come from its composition, mostly hydrogen and helium, vast quantities of gas compacted loosely by gravity rather than packed into dense rock. The beautiful, calm, yellow-beige planet with the most recognizable silhouette in astronomy is, by the standards of density, the least substantial of all the planets. A world vast enough to contain hundreds of Earths, and yet lighter by volume than the water in any swimming pool, we have now established a grammar. Rocky worlds show us their surface chemistry directly. Mercury's mineral gray, Mars's iron oxide red. Worlds with thick atmospheres show us the chemistry of those atmospheres. Venus's sulfuric acid gold, Earth's scattered nitrogen-oxygen blue. Gas giants show us the photochemical products of trace compounds, reacting with sunlight in their upper cloud decks. Jupiter's ammonia and chromophore banding, Saturn's phosphorus-tinged yellow haze. Each planet is applying a filter to sunlight, and the wavelengths that survive that filter are the ones that reach your eye. But as we move to the outermost giants of the solar system, the filter changes completely. The chemistry changes. And the color that results is so specific, so molecularly precise, that it will take us somewhere far more surprising than we expect. The outer solar system is cold in a way that does not simply mean low temperature. It means that molecules that exist as gases in the inner solar system can freeze into solids at these distances, that compounds that are too unstable to persist near the sun's radiation can survive for billions of years in the deep cold, and that the chemistry available for atmospheric reactions is fundamentally different from anything in the inner system. The four outer planets, Jupiter, Saturn, Uranus, Neptune, are sometimes grouped together as gas giants and ice giants. Jupiter and Saturn are the gas giants, built mostly of hydrogen and helium. Uranus and Neptune are the ice giants, built from materials that scientists call ices, water, ammonia, and methane in states of matter that are neither the gases nor the simple crystals of everyday experience, but exotic high-pressure phases that only exist under the crushing conditions deep in a planetary interior. And it is because of one specific molecule, methane, that Uranus and Neptune show the colors that they do. Methane is a simple molecule, one carbon atom bonded to 4 hydrogen atoms. On Earth, methane is a colorless, odorless gas, the same gas that burns in kitchen stoves, that cattle produce, that leaks from thawing permafrost. It absorbs no visible light that human eyes can perceive in the small concentrations we encounter on Earth's surface. But in the thick, cold atmospheres of Uranus and Neptune, methane is present in concentrations of around 2% of the total atmospheric volume, modest by absolute measure, but sufficient to have a dramatic effect on which wavelengths of light escape the atmosphere after sunlight penetrates it. Methane absorbs red light, not a little red light. It absorbs it efficiently across a broad band of red and near-infrared wavelengths. When sunlight enters the atmospheres of Uranus and Neptune, travels down into the cloud layers, reflects off them, and attempts to return to space, the red component of that light has been dramatically reduced. By absorption from the methane it passed through on the way in and on the way out. What escapes to space is the light that was not absorbed, the blue and green and cyan wavelengths. Those are the colors that reach our telescopes. Those are the colors we see. Both Uranus and Neptune appear blue because both of their atmospheres contain methane. That much has been understood for decades. But for decades, a mystery remained. If both planets have similar atmospheric compositions, roughly 80 to 85% hydrogen, 12 to 15% helium, and around 2% methane, why do they look so different from each other? Voyager 2 flew past Uranus in 1986 and Neptune in 1989. The images it returned showed Uranus as a pale, almost featureless cyan green globe, and Neptune as a vivid, deep cobalt blue. For a long time, astronomers assumed that some additional chemical agent was responsible for Neptune's deeper blue, perhaps a greater abundance of methane, or a different distribution of clouds, or an unknown compound that absorbed slightly different wavelengths. In 2022, a research team using observations from the Gemini North Telescope, the NASA Infrared Telescope Facility, and the Hubble Space Telescope published a new atmospheric model for both planets that resolved much of the mystery. The answer was not a mysterious additional absorber in Neptune. The answer was a haze. Both planets have a middle atmospheric layer sitting between the deep cloud deck below and the thin high-altitude haze above that is composed of frozen hydrogen sulfide particles mixed with photochemical haze droplets. This layer is present on both planets, but on Uranus, this haze layer is approximately twice as thick as the equivalent layer on Neptune. Why? The answer, as determined by the same research, comes down to atmospheric dynamics. Neptune is a more active, more turbulent planet than Uranus. Despite being farther from the Sun and receiving less solar energy, Neptune generates significantly more internal heat left over from its formation, and this internal heat drives convection and turbulence throughout its atmosphere. The turbulent mixing in Neptune's atmosphere is more vigorous. It continuously churns methane ice particles up into the haze layer, where those particles coat themselves with haze material and then snow back down into the deeper cloud layers, constantly refreshing the haze and keeping it thin. Uranus, by contrast, has a stagnant, sluggish atmosphere. It generates almost no detectable internal heat. Its atmosphere sits quietly, and without vigorous convection to cycle material through the haze layer, the haze accumulates and thickens. A thicker haze whitens the color it scatters light more broadly, diluting the pure methane blue beneath with a whitish tint that shifts the color towards cyan and pale green. Neptune's thinner haze allows the deeper methane blue to show through more cleanly, producing the richer, deeper blue we observe. Then, in 2024, Patrick Irwin and colleagues at the University of Oxford published a reprocessing of the original Voyager 2 images of both planets using modern calibration techniques. What they found was striking. The true color difference between Uranus and Neptune had been substantially exaggerated by the way the original images were processed in 1986 and 1989. In the original processing, scientists at the time were working without the digital tools that exist today, and the image processing choices that were made partly to enhance cloud features for scientific analysis inadvertently deepened Neptune's apparent blue and lightened Uranus's apparent cyan beyond what a human observer's eye would actually see. In true color, the two planets are considerably more similar than the iconic images suggested. Neptune is still somewhat bluer, and the haze layer explanation still holds. But the dramatic contrast that has appeared in textbooks and posters for 35 years was partially an artifact of processing. This matters because it illustrates something important about how we read planetary color. The colors we see in photographs are not always the colors a human eye would see from a spacecraft window. Telescope images are frequently processed, sometimes to enhance scientific features, sometimes to compensate for instrument sensitivities, sometimes simply to produce images that are visually striking. The history of Uranus and Neptune's perceived color difference is a warning embedded in the science itself. The language of planetary color is real, but learning to read it requires knowing what instrument produced the image and what has been done to the data before it reached you. What the OWIN 2024 reprocessing did not change, what it confirmed is that the underlying mechanism is methane. The methane is real. The haze difference is real. The color difference is real, just smaller in true color than we thought. And the reason both planets are any color at all in the blue-green range, rather than the pale cream of their deeper hydrogen-helium bulk, is because of a molecule that on Earth we associate with cows and swamps and kitchen fires. The universe does not care about our categories. There is one more chapter in the color story of Uranus and Neptune that does not show on any photograph, because it happens deep inside both planets in regions that no spacecraft has ever reached and no light ever escapes from. It is one of the most remarkable predictions in planetary science, supported by high-pressure laboratory experiments here on Earth, and it concerns a color so specific and so culturally loaded that it almost sounds like fiction. Deep inside Uranus and Neptune, at depths where the pressure climbs to millions of atmospheres and the temperatures reach tens of thousands of degrees Fahrenheit, scientists believe that carbon atoms, under those extreme conditions, are squeezed out of the methane-rich mixture they exist in and crystallize into diamond, not traces of diamond, substantial quantities of diamond. And not in a solid crust, but in a liquid state, a diamond rain that falls through the outer layers of the planets and accumulates in a diamond ocean or diamond core around the rocky center of each world. The evidence for this comes from laser-driven shock experiments conducted in laboratories on Earth, in which researchers used powerful lasers to replicate the pressure and temperature conditions believed to exist inside Uranus and Neptune, and then sent X-ray pulses through the compressed material to look for diamond crystal formation. In 2017, a research team at Lawrence Livermore National Laboratory reported clear crystallographic evidence for diamond formation in compressed carbon-hydrogen mixtures at conditions consistent with the deep interior of ice giant planets. The diamond did not simply form, it formed in the presence of a superyonic water phase, and it separated gravitationally, beginning to sink toward the center of the material. This is the rain mechanism, carbon squeezed into diamond crystals that are denser than the surrounding material and fall deeper into the planet. In 2022, further experiments refined the models, confirming that the process is plausible at conditions specific to both Uranus and Neptune. The diamonds are not forming at the cloud tops where we observe the methane. They form far deeper, in a realm of the planet that is effectively unreachable. But they form from the same methane whose presence in the upper atmosphere gives Uranus and Neptune their color. The molecule that paints these worlds blue from the outside is also, under the right conditions, making diamonds on the inside. The same chemistry, expressed at opposite extremes of pressure and temperature, produces two completely different outcomes, a blue sky and a diamond rain, on the same world simultaneously. Uranus and Neptune are wearing their chemistry on the outside in color, and carrying its most extreme consequences in their invisible, unreachable interiors. What we see from Earth is the beginning of the story. What we cannot see is the ending that the chemistry is writing in the dark. And that darkness, the way color can conceal as much as it reveals, the way the surface of a world can be a threshold between the readable and the unreadable, is exactly the principle that the next part of this journey will take further than anything in our own solar system has prepared us for. Because beyond the orbit of Neptune, beyond the edge of the known solar system, there are worlds whose colors are so alien, so specific, and so laden with information that they do not just tell us what those worlds are made of. They tell us what those worlds have been through. And in one extraordinary case, they tell us a story about transformation, about a star that became a planet, and a planet that became something the universe had never made before. There is a question that sits at the center of everything the outer solar system has taught us, and it is a question that sounds simple until you actually try to answer it. The question is this: what color is Uranus? You would think, after decades of space exploration, after Voyager 2's flyby in 1986, after hundreds of images processed and published and printed in textbooks and hung on classroom walls, after the Irwin 2024 reprocessing, after all of it, you would think we would have a definitive answer. The truth is more interesting than any definitive answer would be. The color of Uranus is not simply a property of the planet. It is a relationship between the planet, the sunlight it receives, the instruments that observe it, the choices made in processing the resulting data, and the specific question you are asking when you point a telescope at it. Uranus has a true color, but finding it turns out to be a lesson in how science actually works, and in how carefully we have to read any measurement that comes back to us through layers of technology, processing, and human decision-making. When Voyager 2 passed Uranus in January of 1986, it was traveling at more than 54,000 kilometers per hour. The spacecraft had been in transit for 8.5 years since its launch from Cape Canaveral in 1977. Its cameras and instruments were by that point 8 years old, operating in conditions no engineer on the ground could fully predict, and the team receiving the data was under intense pressure to produce images quickly because the flyby window was narrow and the scientific community was watching. The images that came back were processed to emphasize cloud features. Scientists wanted to see the atmospheric structure of Uranus, not simply its color, and the processing choices that enhanced that structure also altered the color. The result was a very pale, almost featureless blue cyan globe that looked smooth and serene, almost bland compared to Jupiter's riot of color. What the Irwin 2024 study showed was that if you reprocess those same Voyager 2 images using modern calibration methods, matching the Voyager camera sensitivities to modern spectral observations, Uranus becomes noticeably greener and slightly less pale. The planet is still blue-green, methane is still the reason, but the difference between Uranus and Neptune in true color is significantly smaller than the iconic images suggested. Neptune, when reprocessed using the same methods, becomes somewhat paler, less the saturated cobalt of deep ocean water, and more a soft, slightly greener blue. The two planets end up looking like siblings rather than opposites, which, chemically, they are. This revision is not a crisis for planetary science. It is an example of science improving itself, of researchers going back to old data with better tools and finding something closer to the truth. But it does raise a question worth sitting with for a moment. If we have been looking at Uranus and Neptune in slightly wrong colors for 35 years, not dramatically wrong, not wrong in a way that undermined any scientific conclusions, but wrong enough that textbooks worldwide depicted them with an exaggerated contrast. What else are we seeing in planetary images that carries embedded assumptions about processing choices? How much of what we know about the color of distant worlds is the color of the world? And how much is the color of the instrument, the algorithm, the decision made by a scientist in a darkened room trying to make something scientifically useful? This is not a reason for doubt. It is a reason for precision. And precision, in the case of planetary color, has been growing steadily and rapidly since the launch of the Hubble Space Telescope, the Cassini-Huygens mission to Saturn, and most recently, the James Webb Space Telescope. Each generation of instruments sees more clearly, with greater spectral resolution and sensitivity, and each generation of images is processed more carefully and more transparently. The color of a planet in a modern JWST image is a closer approximation of ground truth than any Voyager-era photograph. We are getting better at reading the language. Let us return, now, to the haze difference that explains what color difference remains between Uranus and Neptune, and push deeper into what it reveals, because the story does not end with a thicker haze layer on Uranus. The haze layer tells us something about how the two planets are built inside, and how they got that way. And one of those interior stories is genuinely startling. Uranus is the only planet in the solar system that rotates on its side. Its axial tilt is approximately 98 degrees from the plane of its orbit around the Sun, meaning its north pole points almost directly at the Sun at one point in its orbit, and almost directly away from it, a quarter of an orbit later. The result is the most extreme seasons in the solar system. When Uranus's north pole faces the Sun, the northern hemisphere experiences approximately 42 Earth years of continuous daylight, while the southern hemisphere endures 42 Earth years of continuous night. Then the geometry reverses. Neither pole experiences a conventional cycle of day and night for decades at a time. This extreme tilt is almost certainly the result of a massive collision sometime in the distant past, a giant impact by a body roughly the size of Earth that struck Uranus at an oblique angle and knocked it over. This collision would have been catastrophically violent, and the surprising thing is not that it happened, but that Uranus survived it and remains in the condition we observe today. The collision may also explain why Uranus generates almost no detectable internal heat. Most giant planets radiate significantly more heat outward than they receive from the Sun. They are still cooling from their formation, releasing the gravitational energy from the material that fell together to build them. Uranus radiates almost exactly as much heat as it receives. It appears to have no significant internal heat source. One hypothesis is that the giant impact that tipped Uranus on its side also disrupted the internal structure in a way that created a stable, stratified layer in the planet's deep interior, a layer that acts as a thermal blanket, trapping the internal heat and preventing it from reaching the outer atmosphere. If this is true, then Uranus's sluggish, stagnant atmosphere, the atmospheric dynamics that produce its thicker haze and its paler color compared to Neptune, is a direct consequence of the collision that knocked it sideways billions of years ago. The color of Uranus, the precise pale cyan green that it shows us, may be the visible signature of a catastrophic ancient impact preserved in atmospheric dynamics. Neptune has no such internal heat barrier. Its internal heat drives convection that stirs the atmosphere continuously, keeping the haze layer thin, keeping the methane blue visible at its deepest and richest. Neptune's deeper blue, even in its true color reprocessed form, is the signature of a more dynamically active interior that was, for whatever reason, not hit by a sideways impactor. Two worlds with nearly identical chemistry, showing slightly different colors because of what may have happened to one of them billions of years ago in a collision that left no other visible trace. Color, once again, as a record of history. The atmosphere of Neptune also produces winds that are among the fastest in the solar system, speeds approaching 2 to 1,000 kilometers per hour near the equatorial jet stream, significantly faster than anything seen on Jupiter or Saturn. These winds create the large dark spots, anticyclonic storm systems visible in images of Neptune's disk that come and go over decades. Unlike Jupiter's Great Red Spot, which has persisted for centuries, Neptune's great dark spots appear and dissipate. Voyager 2 observed a large dark spot in 1989. By the time the Hubble Space Telescope looked for it in 1994, it had disappeared. New spots had formed. This dynamism is the same atmospheric energy that keeps Neptune's haze layer thin, that makes it bluer, that makes it visually different from its quieter, tipped neighbor. Now let us go down, not just to the cloud deck, but through it, past it, deeper into the ice giant interiors, because this is where the color story intersects with one of the most extraordinary physical processes in the entire solar system, the diamond rain that both Uranus and Neptune may be generating continuously in their deep interiors. We established in Part 1 that methane in the atmospheres of Uranus and Neptune absorbs red light and gives the planets their blue color. But methane is not only an atmospheric compound on these worlds, it is also a component of the exotic high-pressure material that fills the interiors of ice giants regions where the pressure and temperature are so extreme that our familiar categories of solid, liquid, and gas break down entirely. Picture the layers of an ice giant from the outside in. The outermost layer is the atmosphere we have been discussing: hydrogen, helium, and methane gas, relatively cool, showing us the blue color. Below the atmosphere, pressure begins climbing rapidly. Within a few thousand kilometers below the cloud tops, the pressure reaches tens of thousands of atmospheres and temperatures climb to thousands of degrees Fahrenheit. At these conditions, water, ammonia, and methane, the so-called ices, are compressed into a hot, dense, electrically conducting fluid that behaves like no substance we encounter on Earth's surface. This fluid layer is sometimes called a warm, dense fluid or a superionic layer, depending on the specific conditions. It is not a liquid in the everyday sense, nor a solid. It is something else entirely, something that only exists in the interior of worlds. Within this layer, methane molecules are under sufficient pressure that the carbon-hydrogen bonds within them can be broken by the sheer force of compression. The hydrogen atoms are freed into the general fluid, and the carbon atoms, now liberated from their molecular bonds, seek the most stable configuration they can find. At these extreme pressures and temperatures, the most stable configuration for carbon is diamond. The crystal lattice of diamond is the tightest, most energetically favorable way for carbon atoms to pack together, and under millions of atmospheres of pressure, carbon will find that configuration spontaneously. The diamonds that form are not microscopic dust. Laboratory experiments have suggested they begin as nanodiamonds, tiny crystals, a few nanometers across, but they can grow as they coalesce, and once they form, they are denser than the surrounding fluid. In a gravitational field, denser material sinks, the diamonds fall. They fall through thousands of kilometers of hot, pressurized fluid, and as they sink deeper, the pressure and temperature increase further. Eventually, near the center of the planet, the conditions may be right for diamond to melt, becoming a liquid diamond ocean surrounding the rocky core. The diamonds rain down from above and accumulate in this ocean. Or, in an alternative model, they strike the solid core directly and begin building up a diamond shell around it. Either way, the interior of Uranus and Neptune may contain quantities of diamond that dwarf anything on Earth's surface by factors that are difficult to fully appreciate. The total mass of diamond in Neptune's interior, if the models are correct, may amount to a significant fraction of the planet's total mass. Neptune masses approximately 17 times as much as Earth. Even a few percent of that in diamond would represent a quantity of crystallized carbon so enormous that all the diamonds ever mined on Earth throughout the entire history of human civilization would be invisible by comparison. A speck, a dust grain, a rounding error. This is happening right now. In the interior of Neptune, at this moment, as you are listening to this, carbon atoms are being stripped from methane molecules under pressures. Your body could not survive for a fraction of a second. And those carbon atoms are crystallizing into diamond and falling through a hot fluid ocean toward the center of a world that from Earth appears as a small, beautiful pale blue disk, one that most people can never find with the naked eye, quietly existing in the cold dark of the outer solar system, making diamonds in quantities no jeweler will ever catalog. The color you see, that soft, methane-generated blue, is the entrance to a process so extreme and so productive that it makes the entire surface of the Earth look modest. The universe is not subtle about what it does. It is only subtle about showing us. Let us now take the question of color beyond our own solar system entirely, because the principles we have been building, color as chemistry, color as process, color as history, do not stop at the edge of the Kuiper belt. They apply everywhere, to every world that orbits any star. And when we apply them to the worlds discovered around other stars, the results are simultaneously familiar and completely alien. The first generation of exoplanet discoveries told us almost nothing about color. The early detection methods, Doppler radial velocity measurements, which detected the wobble a planet induces in its host star, and transit photometry, which measured the fractional dimming of starlight when a planet crossed in front of its star, were indirect. They told us a planet was there, gave us its mass or its size, told us its orbital period. They did not tell us what color it was. They could not tell us that. But a second generation of observations, enabled by larger telescopes and more sophisticated instruments, began to change this. Direct imaging, actually photographing a planet by blocking out the light of its parent star with a coronagraph and looking for the much fainter light of the planet itself, can in principle tell us the color of an exoplanet directly, the same way we know the color of Jupiter. And when direct imaging succeeded in capturing the light of gas giants around nearby stars, the results were startling. The most famous example in this context is the planet designated GJ 504b, and we will return to it with the full depth it deserves in later on. But its discovery by the strategic explorations of exoplanets and disks with Subaru program in 2013 was a landmark precisely because it was the first time a gas giant's color was directly observed around a sun-like star that we could point to with confidence. What the instrument showed was not a pale cream or an ammonia white or a methane blue. It was a deep magenta pink remarkable, unmistakable. And the reason it was pink had everything to do with what the planet was, how young it was, and what stage of its existence it had just begun. Before we reach GJ 504b fully, there is another world that deserves attention here because it represents the most extreme expression of chemistry as color, or rather, chemistry as what lies beyond color that has ever been documented. Deep in the Milky Way, approximately 4 to 1,000 light years from Earth, in the constellation Serpens, there is a millisecond pulsar, a neutron star that rotates at extraordinary speed, roughly 172 times per second. It was first observed in 2009 by a research team led by Matthew Bales at Swinburne University of Technology in Melbourne, Australia. The pulsar designation is PSRJ1719-1438, which we will speak as PSRJ1719-1438. But what the team found orbiting this pulsar, announced in the journal Science in August of 2011, was something that had never been seen before. The companion to this pulsar is a planet with a mass close to Jupiter's, but contained within a volume approximately 40% of Jupiter's volume. The density required to pack Jupiter's mass into 40% of Jupiter's volume is roughly 20 times the density of Jupiter itself. For reference, Jupiter's average density is approximately 1,326 kilograms per cubic meter. The companion planet's density comes out to approximately 23,000 kilograms per cubic meter. For further reference, the density of Diamond on Earth is approximately 3,500 kilograms per cubic meter. The companion planet is denser than Diamond, roughly 6 or 7 times denser. How do you produce a planet that dense? The answer, which Bales and colleagues worked out in their 2011 paper, is that you start with a star. Specifically, a white dwarf, the dense remnant left when a star like our Sun exhausts its nuclear fuel and ejects its outer layers. White dwarfs are already extremely dense, comparable to packing the mass of the Sun into an object roughly the size of Earth. The white dwarf in this case was in a tight orbit around the millisecond pulsar. The pulsar's intense gravitational field and radiation environment gradually stripped the outer layers of the white dwarf away, a process called ablation. Mass was transferred from the white dwarf to the pulsar, which spun up as it gained angular momentum. This is how millisecond pulsars form in the first place, by accreting mass from a companion and being spun up to extraordinarily rapid rotation rates. The ablation continued until the outer hydrogen and helium layers of the white dwarf had been completely stripped away. What remained was the white dwarf's core, the innermost material that had never been expelled, the original carbon-oxygen core of the original star. And this carbon-oxygen core, under the influence of the pulsar's crushing gravity and the cooling that followed its stripping, carbon crystallized into a structure consistent with Diamond. The planet PSRJ1719-1438b is, according to the best current models, composed primarily of crystalline carbon, a form of matter that is structurally related to Diamond, but exists at densities far greater than any diamond on Earth. It is the corpse of a star that was eaten from the outside in by its companion pulsar, ground down to its crystalline core, and left behind as a planetary mass remnant orbiting the object that devoured it. It completes one orbit of its pulsar every 2.1 to 7 hours, at a distance from the pulsar that would fit within the volume of our Sun. The entire orbit planet and pulsar could fit inside the Sun with room to spare. What color is PSR J1719-1438b? That question is almost a category error. Diamond is transparent to visible light and colorless in its pure form on Earth. The planet does not shine by reflecting visible light from a star in the way that Jupiter or Neptune does. The pulsar it orbits is a neutron star that emits primarily in radio waves and X-rays, not in visible light. In visible light, the planet would be essentially invisible, a dark, incredibly dense crystalline object orbiting a radio-emitting neutron star in deep space, radiating no visible light of its own in any meaningful quantity. What we know of it comes entirely from the radio timing variations of the pulsar, the way the pulsar's radio pulses shift in timing as the planet moves around it, pulling the pulsar very slightly toward and away from Earth and producing a Doppler effect in the arrival time of the pulses. This world has no color. In the ordinary sense, it wears only physics. It exists in a frequency range we cannot see, around a star we cannot look at without specialized equipment, in a darkness 4,000 light-years away, going about its 2-hour orbit in silence. And it is made of something so specific, so chemically extraordinary, that the only way to understand it is to trace the entire history of the star it used to be and the violent process that stripped it down to its core. That history, a star becoming a planet, through the violence of pulsar accretion, is the most dramatic color transformation in the known universe. From a glowing stellar object radiating light in every direction to a dark crystalline solid radiating nothing but its own gravitational presence. From a star to a diamond, the color stripped away entirely, leaving only the structure. And this is where the color story begins to reveal something deeper than chemistry. Color, for planets, is always a product of interaction, a product of the relationship between a world and its star. Mercury is gray because there is not enough atmosphere to mediate that relationship. Venus is golden because its clouds take that relationship and distort it entirely, hiding the surface and presenting the chemistry of its sky instead. Mars is red because its relationship with water and oxygen led to rust, and its relationship with sunlight is now a relationship with iron oxide dust. Jupiter and Saturn are colored by the photochemical products of sunlight acting on their upper atmospheric gases. Uranus and Neptune are colored by methane, a molecule that exists in their atmospheres specifically because the outer solar system is cold enough to allow it. And PSR J1719-1438b has no color in visible light because it has no relationship with visible light. Its star does not produce visible light in the conventional sense, and the planet does not reflect any. It has been removed from the ordinary conversation between world and star that produces color everywhere else. It exists outside the language entirely. This is the edge of the solar system's color story. The familiar inner planets, the gas giants, the ice giants, the diamond rain, all of it exists within a framework where sunlight is the narrator and chemistry is the translator. As long as a planet orbits a star that produces visible light, as long as that planet has an atmosphere or a surface that absorbs and reflects specific wavelengths, it will have a color. The color will be the signature of its chemistry. The chemistry will be the signature of its history. But there are worlds beyond the solar system that take this principle further than anything we have seen so far. Worlds whose colors are so strange, so specific, and so deeply informative that they feel like the universe deliberately showing off. And there is one world in particular, 57 light-years away, glowing in a color that almost no planet ever shows. A world whose color is the direct readout of its own birth. A world that is still radiating the heat of its own creation, because it has only been alive for a cosmically brief moment, and it has not yet had time to cool down. That is where we are going next. Part 3: Worlds that glow from the inside out. 57 light-years from Earth, in the constellation Virgo, there is a star that looks unremarkable. It is a G-type main sequence star, the same broad category as our own Sun, designated 59 Virginis, or in the catalog notation used by planet hunters, GJ 504. Under exceptionally dark skies, you can technically see it with the naked eye. It appears as a faint, ordinary point of light, the kind of star you pass over when you are scanning for something more interesting. Nothing about it suggests that it is hosting a world whose color should not exist. In 2013, a team working under the strategic explorations of exoplanets and disks with Subaru program used the Subaru telescope on Mauna Kea in Hawaii to obtain direct images of the planetary system around this star. Direct imaging of exoplanets is extraordinarily difficult. Planets are billions of times fainter than the stars they orbit. To image one directly, you have to block out the starlight with a coronagraph, and then search the surrounding field for any point source that moves with the star over time, confirming it is gravitationally associated rather than a background object. Most planets cannot be directly imaged at all with current technology because they are too close to their stars and too faint. You need a planet that is either very large or very bright, and the brightness of an exoplanet depends primarily on two things: how much starlight it reflects and how much heat it radiates from its own interior. The planet that emerged from the Subaru data around GJ 504 was visible not because it was bright with reflected starlight. It was visible because it was glowing with its own heat. And the light the glow produced, when measured by the instrument, was concentrated in the near-infrared wavelengths, with a peak that fell in the range that a human visual system, if it were sensitive enough to detect, it would perceive as deep magenta, pink. The color of a heated object that is not quite hot enough to glow red, radiating in the longer wavelength part of the visible and near-infrared spectrum. A dark cherry blossom, as one member of the Discovery team described it. A dull magenta, a color that planets in our solar system, all of them billions of years old, all of them long since cooled from their formation, do not show. The planet is known as GJ 504b. Its mass is approximately 4 times the mass of Jupiter. Its radius is slightly larger than Jupiter's, roughly 1.2 times Jupiter's diameter. It orbits its parent star at a distance of approximately 43.5 astronomical units, nearly 9 times the distance from Jupiter to our Sun. At that distance, it receives very little starlight, and the reflected starlight it does receive is a minor contribution to the total light we detect from it. The dominant source of detectable emission from GJ 504b is thermal, its own body heat, radiating outward, because the planet has not yet finished the process of cooling down from the tremendous heat of its formation. The age of the GJ 504 star system is estimated at approximately 160 million years. To put that in the context of solar system timescales, our own solar system is approximately 4.6 billion years old. GJ 504 is roughly 3.5% as old as our solar system. It is cosmically newborn. Our sun formed, our planets formed, the heavy bombardment that scarred the moon and reshuffled the inner solar system ended. Life appeared on Earth. The first oxygen-generating bacteria transformed our atmosphere. Multicellular life evolved. Complex animals appeared. Vertebrates crawled onto land. Dinosaurs arose and ruled for more than 150 million years, and they were wiped out. All of that happened in the time that GJ 504b has been cooling from its formation temperature toward a future equilibrium it has not yet reached. A planet as massive as GJ 504b forms from the gravitational collapse of gas and dust in the protoplanetary disk around its young star. When material collapses under gravity, it releases gravitational potential energy as heat, the same principle that causes a falling object to warm when it hits the ground, but on a scale of quadrillions of tons of gas crashing inward at speeds that compress the infalling material to temperatures of tens of thousands of degrees Fahrenheit. The newly formed giant planet is extremely hot. Over time, it cools by radiating heat outward into space. This is the same process that has been occurring in Jupiter for 4.6 billion years. Jupiter still radiates about 1.7 times as much energy as it receives from the Sun, evidence that it is still cooling. But Jupiter has had 4.6 billion years to cool. GJ 504b has had 160 million years. At 160 million years old, GJ 504b still carries a substantial thermal load from its formation. Its effective temperature, the temperature that represents the heat it is radiating outward, is approximately 459 degrees Fahrenheit. This is the temperature of an oven set at its very highest conventional setting. It is hot enough to incinerate most organic compounds on contact, and this residual heat is what makes the planet glow in the near-infrared, what gives it its magenta color, what allowed the Subaru telescope to detect it in the first place. But the magenta is not simply a glow from heat. If it were purely thermal radiation, the exact peak wavelength of the color would be determined by the temperature alone through the physics of blackbody radiation, the same law that tells you a heating element first glows dull red, before orange, before yellow-white, as it gets hotter. At 459 degrees Fahrenheit, a perfect blackbody would peak in the near-infrared, just beyond the visible range of human vision. The slight magenta tint, the fact that some of the emission is at wavelengths visible to human eyes rather than entirely in the infrared, comes partly from the thermal emission extending into the red end of the visible spectrum, and partly from the absorption characteristics of the planet's atmosphere. GJ 504b almost certainly has a methane-containing atmosphere, similar in broad composition to Jupiter's, but at a much higher temperature. At 459 degrees Fahrenheit, the atmospheric chemistry is different from Jupiter's. Methane absorbs strongly at specific infrared wavelengths, including bands near 1.6 and 2.2 micrometers. When thermal radiation from the planet's hot interior passes through the atmosphere on its way out to space, these methane bands absorb specific portions of the near-infrared spectrum. The result is that the radiation escaping from the planet has gaps, wavelength ranges that have been removed by methane absorption, and what remains is a modified spectrum whose peak shifts in a way that moves it closer to visible wavelengths, specifically toward the red and the deep red that grades into magenta. The methane that makes Uranus and Neptune blue by absorbing red sunlight from outside is here helping to sculpt the color of GJ 504b from the inside out by shaping which portions of the planet's own thermal emission can escape. There is a further complexity. GJ 504b, at its current temperature and age, may have fewer clouds than typical giant planets of similar size and mass. Observations by the Discovery team suggested the near-infrared colors were consistent with a relatively cloud-free or partially cloud-free atmosphere, at least in the near-infrared wavelength range observed. This matters because thick clouds, if present, would reflect and scatter radiation in ways that could obscure the thermal glow from below. A clearer atmosphere means more of the deep thermal emission can escape upward, contributing to the planet's visible glow. The magenta of GJ 504b may be, in part, the color you see when a giant planet's birth heat shines through a relatively transparent window in its young atmosphere. Consider the timeline being compressed into that one color. 160 million years ago, a disk of gas and dust collapsed around a young star 57 light-years from Earth. Gravity pulled matter inward, and as it converged, it heated. A giant planet assembled itself in the outer disk, far from its star, in a region where, according to our conventional models of planet formation through core accretion, a planet this large should have struggled to form. The standard core accretion model proposes that planets form by first building a solid core of ice and rock, which then attracts a gaseous envelope. At 43 astronomical units from the star, there is so little solid material available, and the orbital timescale is so long that building a massive enough core to capture a Jupiter-scale gas envelope should take far longer than the disk typically persists. GJ 504b, either formed by an alternative mechanism, perhaps gravitational disk instability, in which a massive disk fragment collapses directly into a gas giant without needing a preformed solid core, or formed closer to the star and migrated outward through gravitational interactions. Or the current models of planet formation need revision. None of these explanations is fully settled. The planet's existence at its current location is, itself, a challenge to planetary formation theory. And it glows magenta as evidence of that origin, still warm from the violence of its creation, still radiating the heat of the collapse that made it visible across 57 light-years, not by reflected starlight, but by the light of its own infancy. It is a planet you are seeing not by illumination, but by birth heat. Its color is the color of becoming. The discovery of GJ 504b in 2013 was, at the time of its announcement, one of the lowest mass planets ever directly imaged around a sun-like star. Since then, the field of direct imaging has matured, and multiple other young giant planets have been directly imaged around their host stars. Each one that has been characterized thermally shows the same principle. Young planets glow because they are hot, and their colors, in the near-infrared and visible red, are determined by the combination of their formation heat and the molecular absorption characteristics of their atmospheres. As they age, they cool, their near-infrared emission fades. The thermal glow retreats into longer and longer wavelengths, eventually becoming too cold and too red-shifted for direct imaging. In a few 100 million years, GJ 504b will be indistinguishable from a cold, dark, Jupiter-like world, reflective only by starlight, colored only by cloud chemistry and atmospheric absorption of its star's radiation, no longer self-luminous in any way that human instruments could easily detect from this distance. We are watching it while it still glows, We are seeing its color, while it still has something to say about its origin. In astronomical terms, our view is fleeting. In human terms, it will last longer than any civilization that has ever existed. That coexistence of timescales, the planet's geological infancy, and our own civilizational history is one of the stranger facts in this story, and we do not have time to get lost in it here, because there is one more world in this part of the journey that demands our full attention, a world so physically extraordinary that the adjective extraordinary barely captures it. A world not glowing from birth heat, not colored by atmospheric chemistry, not reflecting the light of a living star. A world that, depending on your definitions, should not exist at all. We have already established the background. A millisecond pulsar spinning 172 times per second, 4,000 light years away, in the constellation Serpens. Designation PSRJ 1719-1438, and orbiting it, a planetary mass object discovered through radio timing, announced in Science in August 2011, now understood as one of the most extreme objects in the known catalogue of planetary mass bodies. But let us go back further before the pulsar, before the stripping, before the crystallization, to understand what this world used to be, because the history is what makes the current reality comprehensible. Many stars in the galaxy exist in binary systems, two stars gravitationally bound to each other, orbiting their common center of mass. Most binary pairs orbit each other at comfortable distances and do not interact in ways that fundamentally alter either member's evolution. But in some binary systems, the stars are close enough, and one of them is massive enough that when the larger star ends its life and collapses into a neutron star or black hole, the surviving companion continues its own stellar evolution and eventually transfers mass to the compact object. This mass transfer is the engine of some of the most energetic phenomena in the universe: X-ray binaries, nova explosions, millisecond pulsars. In the system we are describing, the neutron star, the pulsar, accreted mass from its companion star over an extended period. As mass fell onto the neutron star, it spun up, gaining angular momentum from the infalling material. This is how millisecond pulsars are created. They are called recycled pulsars because they have been spun back up to rapid rotation by accretion. The companion star, meanwhile, was losing its outer layers to the neutron star, being stripped away from the outside in. This process is called ablation, and it is extremely slow by human standards, but extremely fast by stellar standards. As the ablation proceeded, the companion star's mass dropped below a critical threshold. Stars burn hydrogen in their cores because the gravitational pressure is sufficient to sustain nuclear fusion. Below a certain mass, a star can no longer sustain fusion, and it becomes a white dwarf, a dense, inert remnant of roughly Earth-sized volume containing the mass of the original stellar core, cooling slowly over billions of years. The companion to the pulsar crossed this threshold and became a white dwarf, but the ablation did not stop. The pulsar's radiation and gravity continued, stripping the white dwarf's outer layers, the hydrogen and helium that form the outer envelope of even a dead star. Layer by layer, the white dwarf was reduced, and what remained, once the outer envelope was gone, was the white dwarf's inner core, the most compressed, most processed material from the star's nuclear burning history, and that material was carbon and oxygen. Under the gravity of this entire sequence of events, under the compression of the original stellar collapse and the subsequent ablation, the carbon-oxygen core crystallized. This is actually the standard fate of white dwarfs. They cool over billions of years and eventually crystallize, forming a form of crystalline carbon that is structurally similar to diamond. Astronomers refer to this as a diamond white dwarf, an old, cool white dwarf that has crystallized throughout its interior. The companion to PSR J1719-1438 had that process accelerated enormously by the stripping, because instead of a white dwarf slowly cooling over billions of years and then crystallizing, the ablation removed the outer layers, reduced the thermal buffering, and left behind a dense, rapidly cooling crystalline core in an extreme gravitational environment. This crystalline remnant, the stripped core of a former star, now a planetary mass body, orbits its pulsar in 2.17 hours at a distance of approximately 600,000 kilometers. 600,000 kilometers. For comparison, the radius of the Sun is approximately 696,000 kilometers. The entire orbit of this planet pulsar system could fit within the volume of our Sun with only the barest margin. If you were to place our Sun at the pulsar's location, the planet would be orbiting deep inside the Sun, skimming through the solar interior, completing more than 10 orbits per day, surrounded by nuclear fusion reactions and temperatures of over 27 million degrees Fahrenheit. Yet there it is, a crystalline carbon world, nearly the mass of Jupiter, orbiting in 2 hours, smaller in diameter than any other planet of similar mass, so dense that every cubic centimeter of it contains more matter than any natural non-neutron star substance on Earth. A world denser than diamond, moving faster in its orbit than most satellite spacecraft orbit the Earth, around a star that was itself once a dying red giant spinning down, now a lighthouse of radio pulses swept across the galaxy 172 times per second. The color of this world, as we established earlier, is not expressible in the language of visible light. But its existence is a testament to something that runs through every world we have examined in this journey. Color, or the absence of it, is always a consequence of history. Mercury is gray because it never built an atmosphere. Venus is golden because its atmosphere became a sulfuric acid ocean in the sky. Mars is red because it rusted as it died. Uranus and Neptune are blue because they kept their methane while the rocky planets lost theirs. GJ 504b is magenta because it has not yet cooled from its birth. And PSR J1 719-1438b has no visible color at all because it has been stripped of everything: atmosphere, stellar envelope, photosphere, every layer that a body normally uses to interact with visible light, leaving only the crystal underneath. It is the most radical form of planetary simplicity imaginable, a world reduced to its core, to its absolute essence, to the chemistry that had been building quietly inside a star for the entirety of that star's existence, now exposed to the universe with nothing above it to soften or obscure or colorize. And between these two extremes, the pink glow of a newborn world that has barely begun to exist, and the invisible crystalline silence of a world stripped down to nothing but its carbon skeleton, there is a third exoplanet that completes this trio. A world that has been many things in its existence. A world that was once called a diamond planet, that was stripped of that designation, that was then given something stranger and more violent in its place, and that, as of 2024, has been understood in a way that makes it unlike anything else we have visited tonight. 55 Cancri E, also designated 55 CNC E in catalog notation. Located approximately 41 light-years from Earth in the constellation Cancer. Its host star, 55 Cancri A, is a binary star, a G-type star, similar to our Sun, paired with a smaller red dwarf companion. 55 Cancri E orbits the G-type primary star at a distance of approximately 0.015 astronomical units, roughly 1/60th of the Earth-Sun distance. It completes one orbit every 17.5 hours. Its year is shorter than most people's working week. In terms of size and mass, 55 Cancri E is classified as a super-Earth. Its radius is approximately 1.95 times Earth's radius, and its mass is approximately 8.8 times Earth's mass. It is rocky. Its bulk density is consistent with a composition primarily of silicates and other rocky minerals, similar in general category to Earth, but with a mean density somewhat lower than Earth's, which suggests the presence of lighter elements or an extended envelope. The planet is tidally locked to its host star, meaning the same face always points toward the star, and the same face always points away. It does not rotate relative to its Sun, the way Earth rotates relative to ours. One hemisphere bakes in permanent, unrelenting stellar radiation. The other sits in permanent darkness. For years, 55 Cancri was famous for a specific and spectacular claim that it might be a diamond planet. The hypothesis originated from analysis of the elemental abundances of its host star. Stars and the planets that form around them are built from the same reservoir of material, the gas and dust of the protoplanetary disk. If you measure the chemical composition of the star, you can make inferences about the composition of its rocky planets. The host star, 55 Cancri A, was measured to have a carbon-to-oxygen ratio that, in some earlier analyses, appeared unusually high, closer to the threshold where carbon-rich chemistry might dominate the solid materials forming in the disk. If a planet forms in a carbon-rich environment rather than the oxygen-rich environment in which Earth formed, the mineralogy is completely different. Instead of silicate minerals, the oxides of silicon, iron, and magnesium that make up most of Earth's mantle and crust, a carbon-rich planet would form from silicon carbide, graphite, and possibly diamond at depth, where pressures are high enough to convert carbon into its most compressed crystalline form. Researchers at Yale University, in a paper published in 2012, suggested that if 55 Cancri's interior composition reflected the high carbon-to-oxygen ratio implied by the stellar measurements, then a significant fraction, perhaps 1/3 of the planet's mass, could consist of diamond and graphite. The surface, they proposed, might be covered in graphite and diamond, rather than the water and silicate rock that cover Earth. The diamond planet hypothesis was sensational. It spread rapidly through scientific journalism and became one of the most widely cited examples of exotic exoplanet chemistry. It was a genuine and scientifically grounded hypothesis at the time it was proposed. But it had a weakness. The carbon-to-oxygen ratio of 55 Cancri A turned out to be more uncertain than initial measurements suggested. Later, more precise spectroscopic analyses of the star produced values closer to solar ratios not extraordinarily carbon-rich. If the star is not unusually carbon-rich, the argument for a carbon-dominated planet interior collapses. The interior composition of 55 Cancri remained uncertain. The diamond label persisted in popular science writing even as the scientific underpinning eroded. Then, in 2016, Spitzer Space Telescope observations of the planet's thermal emission suggested its dayside temperature was unexpectedly variable, over timescales of months varying from roughly 3,300 degrees Fahrenheit to over 4,200 degrees Fahrenheit. This was strange for a tidally locked world where you might expect the dayside to maintain a roughly constant equilibrium temperature. The variability suggested something dynamic, possibly volcanic activity, possibly changing cloud patterns, possibly atmospheric variations. The image of a static diamond surface gave way to something more dynamic, more molten, more alive, and then came JWST. In May of 2024, a team led by Renyu Hu of the Jet Propulsion Laboratory published results in the journal Nature based on JWST observations of 55 Cancri E using the near-infrared camera and the mid-infrared instrument, NIRCam, and MIRI, covering a spectral range from 4 to 12 micrometers. They measured the thermal emission spectrum of the planet, the pattern of heat radiation from its dayside as a function of wavelength, obtained during secondary eclipse events when the planet passed behind its star, and the difference between star plus planet flux and star-alone flux revealed the planet's own emission. What the spectrum showed was decisive on one point. 55 Cancri E is not simply a bare lava world, a rock surface with a thin veneer of vaporized minerals as the only atmosphere. The vaporized rock atmospheric model, which had been one of the leading hypotheses, predicts a specific spectral signature based on the expected composition of rock vapor. The JWST spectrum did not match that model. Instead, the spectral shape was consistent with a genuine volatile atmosphere, an atmosphere made of real gaseous molecules, with their own vibrational and rotational spectroscopic signatures, specifically an atmosphere rich in carbon monoxide, carbon dioxide, or some combination of both, possibly with other volatile compounds. The paper concluded that 55 Cancri E almost certainly has a secondary atmosphere. Secondary meaning it was not the original primordial atmosphere from formation, but a replacement atmosphere that accumulated later, and that this atmosphere is being generated by and sustained by a global magma ocean. The planet's surface, on its permanent dayside, is almost certainly covered in molten rock. Temperatures on the dayside reach approximately 4,340 degrees Fahrenheit at maximum, hot enough to melt virtually any silicate mineral and many metals. At these temperatures, the surface is a glowing, roiling ocean of liquid rock, almost certainly convecting, erupting, spattering, turning over continuously as it receives the unrelenting radiation of a sun that never sets. The gases, carbon monoxide, carbon dioxide, and likely other volatile compounds, including possibly sulfur dioxide, are dissolved in the magma ocean the same way carbon dioxide dissolves in the oceans of Earth. As the magma convects and churns, these dissolved gases continuously exsolve and bubble out, rising through the melt and escaping into the atmosphere above. The atmosphere is not static. It is constantly being produced by volcanic outgassing from the ocean below and simultaneously being lost to space at the top, where the planet's relatively weak gravity and the intense stellar radiation are continuously stripping material away. The atmosphere of 55 Cancri E is in a constant state of dynamic replenishment, a volcanic breath pulled out of a planet-wide lava ocean and pushed up through the atmosphere and away into space, over and over, indefinitely. This is a world that destroyed its original primordial atmosphere through the same stellar irradiation that drives its volcanic activity, and then grew a replacement atmosphere from its own molten interior. It literally built a second atmosphere out of its own body. From the inside, the star took one atmosphere away. The planet made another. There is also an additional layer of complexity that the JWST data revealed. Further observations, reported in the same period, showed that the emission from 55 Cancri E varies significantly over timescales of days. Both the brightness and the spectral shape of the dayside emission change in ways that suggest the atmosphere itself is varying. One hypothesis is that the volcanic outgassing rate fluctuates as the magma ocean convects unevenly, producing bursts of more intense atmospheric generation at certain times and quieter periods at others. Another possibility is that large-scale atmospheric dynamics weather, if you can call it, that on the dayside produce temporary concentrations or dispersals of the absorbing gases that change how the atmosphere looks to our instruments. Either way, 55 Cancri E is not a stable, predictable world. It is a world in continuous geological and atmospheric motion, producing a different spectrum from day to day. What color is 55 Cancri E? In visible light, as observed from a hypothetical spacecraft at close range, the dayside of the planet would almost certainly appear white-orange, the incandescent glow of molten rock at thousands of degrees Fahrenheit, the same color as the interior of a blast furnace, the same color as a steel foundry in the moment of the pour. The night side, in permanent darkness and receiving almost no heat from the star, would be much cooler, perhaps cool enough to have solidified lava, flows in places, and would appear very dark, with scattered orange-red patches where heat conducted from the interior or from the atmosphere slowly warms the surface above the solidification temperature of rock. The atmosphere itself, if you were flying through it, would be thick with carbon monoxide and carbon dioxide gas, both of which are invisible to human eyes. What you would see through this atmosphere from the surface, if you were standing somewhere near the terminator line between the permanent day and permanent night hemispheres, would be a sun that never moves, hanging enormous and scorching in the sky directly ahead of you in the daytime direction, and behind you an eternal dark plane that gradually fades from orange glowing rock near the terminator to black in the deep night side. The sky near the sun would be glowing brilliantly through the carbon dioxide atmosphere with an orange-white tint. The horizon in other directions would be the color of cooling lava. It is not a diamond surface. It never was, as far as the best current evidence can tell us. The earlier hypothesis was not wrong in spirit. It correctly identified that this planet existed in a chemically extreme environment, unlike Earth. But the specifics were wrong. The reality is stranger than the hypothesis. A diamond is static, cold, crystalline, hard, perfect. 55 Cancri E is none of those things. It is liquid, dynamic, volcanic, breathing, continuously destroying and rebuilding itself in a cycle driven by the irresistible energy of a star 6 times closer than Mercury is to our own sun. A diamond would be swallowed by what 55 Cancri actually is. The JWST discovery of 55 Cancri E's secondary atmosphere was one of the most significant results in exoplanet science in 2024. It was the first rocky exoplanet for which a genuine volatile atmosphere had been definitively identified, not a primordial gas envelope like the hydrogen and helium atmospheres of gas giants, but a secondary atmosphere generated geologically. The same kind of atmosphere that Earth, Venus, and Mars all have in different forms. It demonstrated that rocky worlds can sustain atmospheres even in extreme environments through the mechanism of continuous volcanic replenishment. And it changed the way scientists think about what kind of planets might be identifiable by their atmospheric signatures in future observations. The color of 55 Cancri E, the white-orange glow of a lava world wearing a volcanic atmosphere, is, in a sense, the color of geological process laid bare. On Earth, the volcanic processes that produce our secondary atmosphere, the degassing of the mantle, the eruption of carbon dioxide and water vapor, and sulfur compounds from volcanoes happen at the surface locally and sporadically. They are hidden beneath oceans and ice and rock, and the vast dilution of our thick, evolved atmosphere. On 55 Cancri E, the same processes are happening across the entire planet's surface simultaneously, continuously, at temperatures that are off any scale relevant to human experience. The planet is wearing its geology on the outside, in color, glowing with it, breathing it into the sky above. 3 exoplanets, 3 completely different color stories. GJ 500 4b, glowing magenta with birth, heat, and atmospheric methane, a world that is visible precisely because it is young and has not yet learned to be subtle. PSR J1719-1438b, colorless invisible light, a crystalline carbon remnant, orbiting a pulsar, the stripped and exposed core of a former star, so dense that color as a concept barely applies to it. And 55 Cancri, the lava world that was once called a diamond, white-orange, with molten rock and volcanic breath, building and rebuilding its own atmosphere from the inside, refusing to be simplified by any one description. What these 3 worlds share is not their chemistry or their appearance or their location. What they share is the principle that has been building throughout this entire journey. Color, or the specific absence of it, is always the direct readout of what a world has been through, what process formed it, what it is doing right now, what it is surviving. You cannot separate the appearance of a planet from its biography, because the appearance is the biography written in light or in the dark where light cannot go. At whatever temperature and pressure and chemistry the universe has delivered to that particular point in space, at that particular moment in cosmic time. That principal color, as biography, takes on its fullest and most personal meaning when we turn from these exotic, distant worlds and face the one we have lived on for our entire existence without truly seeing it. Because there is one planet in this story whose color is the strangest thing we have encountered. Not strange in the way of a planet made of crystalline carbon, or a world radiating birth heat in magenta, or a lava ocean breathing its own volcanic atmosphere. Strange in a quieter, more specific way. Strange because it requires something that none of those other worlds have managed to produce, and that the universe has provided almost nowhere else that we can confirm. Strange because it is green. You are made of the rarest color in the known solar system. Not in the sense that your body glows green, it does not. But the carbon in your cells, the oxygen you breathe, the nitrogen in your proteins, the phosphorus in your DNA, a significant fraction of those atoms passed through organisms that produced or depended on green light for their energy cycles before they ended up in you. You are downstream of chlorophyll. You are the product of 400 million years of green chemistry continuously running on the surface of a rocky world that, from a distance of several million kilometers, shows that green is a measurable spectral feature imposed on the color of a continent. No other confirmed world in the solar system shows this. There is not another planet within the reach of any current telescope that we know has an inhabited surface, an actively photosynthesizing biosphere, a green patch visible from space that is the color not of a rock or a gas or a cloud, but of a living organism covering hundreds of millions of square kilometers of land surface. Earth's green is unique in the catalogue of observed solar system planets. And understanding why it is there, what sequence of events, what precise combination of chemistry and temperature and time and accident had to occur for it to appear at all, reveals something about the planetary color story that the previous three parts of this journey have been building toward without fully stating. Earth's green is not just a color, it is a convergence. It is the point at which chemistry, time, temperature, water, geology, and biology all aligned and produced a result visible from space. And the fact that it has survived, that it is still here, still covering continents, still measurable from orbit, still coloring the spectral signature of Earth's reflected light with the specific absorption pattern of chlorophyll, is not guaranteed. It is contingent. It could have been otherwise. And in understanding why it is here, we understand something about what planetary color, taken as a whole, is really measuring. Let us go back to the beginning of Earth's green, not the beginning of Earth itself, but the moment when the chemistry that produces green first appeared on this planet. For the first billion or so years of Earth's existence, there was no green on the surface. Earth was a world of dark volcanic rock and shallow oceans, and possibly some orange-brown mats of early chemotrophic microbes, organisms that generated energy from chemical reactions rather than sunlight. The atmosphere was almost devoid of free oxygen. The land, such as it was bare rock, abraded by wind and water, uncolonized by any photosynthetic organism. The planet was not green. Then, approximately 3.4 to 3.5 billion years ago, evidence in the rock record suggests that the first photosynthetic organisms appeared cyanobacteria, which are still living today, still coloring ocean surfaces, still coating rocks in thin microbial films in environments across the planet. These organisms evolved a molecular machine, the photosystem that could absorb specific wavelengths of sunlight and use the captured energy to split water molecules, liberating oxygen gas as a byproduct and using the hydrogen extracted from water to power the construction of organic molecules from atmospheric carbon dioxide. Chlorophyll is the primary light-absorbing molecule in photosynthesis. It is a large, organic molecule containing a magnesium ion at its center, surrounded by a ring structure called a porphyrin ring, connected to a long hydrocarbon tail. Chlorophyll absorbs very efficiently in the blue and red regions of the visible spectrum, the wavelengths that deliver the most useful energy for the photosynthetic reactions. It absorbs poorly in the green region. Green light bounces back off chlorophyll molecules rather than being absorbed. This is why chlorophyll is green. Not because it generates green light, but because it reflects green light after absorbing the other colors it needs. The green we see in a leaf is the leftovers of the solar spectrum after the chemistry has taken what it needs. For approximately 2 billion years, photosynthetic organisms existed primarily in the oceans. They colored parts of the ocean surface green or blue-green with microbial blooms, and over time they transformed the atmosphere from a reducing, oxygen-poor environment to an oxidizing one through the accumulation of the oxygen they exhaled. The Great Oxidation Event, approximately 2.4 billion years ago, is the moment this oxygen accumulation became geochemically significant, permanently changing the chemistry of the atmosphere, rusting many minerals at the surface, and creating the conditions that eventually allowed more complex life forms to evolve. But the land surface of Earth remained mostly bare rock for another 2 billion years after the first photosynthetic microbes evolved. It was not until approximately 470 million years ago that plants, the descendants of aquatic green algae, colonized the land. And it was not until 300 to 360 million years ago, in the Carboniferous period, that forests became widespread enough to cover significant fractions of the continental land surface. The green that is visible in photographs of Earth from space, the green that spectroscopically identifies Earth as a biosphere-bearing world, is a feature that has existed in its current form for only a fraction of Earth's history. It took approximately 4 billion years of biological evolution, 2 mass extinctions, the invention of woody vascular tissue and root systems and seed reproduction, and the colonization of every available continental surface before the green became a planetary scale feature, and even then, it very nearly vanished. The Permian-Triassic extinction event approximately 252 million years ago killed an estimated 90 to 96% of all marine species and approximately 70% of all terrestrial vertebrate species. Estimates suggest that land plant diversity collapsed dramatically during the same event. The Cretaceous-Paleogene extinction 66 million years ago, which ended the reign of non-avian dinosaurs, also disrupted global vegetation patterns significantly. Each time, the green recovered. Life, as we noted when describing Earth's color from space in Part 1, is stubborn, but the recovery was not instant. There were intervals measured in tens of thousands to hundreds of thousands of years when the green was diminished, when the continental surfaces showed more brown and gray, when the chlorophyll signature in Earth's reflected spectrum would have been weaker. The green is here today because life has won, so far, every battle it has faced on this planet, and the fact that it is winning is measurable from space. This is not a metaphor. Modern satellite instruments can measure the total chlorophyll content of Earth's land surface in real time using the spectral signature of chlorophyll in reflected light. This measurement, called the Normalized Difference Vegetation Index, or NDVI, by its acronym, is one of the most routinely obtained and scientifically useful Earth observation products in existence. It maps where vegetation is, how dense it is, and how it is changing seasonally or due to drought, fire, deforestation, or regrowth every year. Satellites produce global maps of Earth's green, tracking the pulse of the biosphere across every continent and every season. From space, Earth's biosphere breathes visibly. In the Northern Hemisphere's summer, the NDVI values surge across North America, Europe, and Asia as forests and grasslands reach peak photosynthetic activity. In the Southern Hemisphere's summer, the pulse shifts south. The Amazon basin maintains near constant deep green year-round. The Sahara and the Arabian Peninsula maintain near constant bare rock brown. The seasonal expansion and contraction of the green band across middle latitudes is a planetary scale oscillation of biological activity, measurable in the spectral properties of reflected light, readable by any instrument sensitive enough to detect it. If a civilization in a distant star system were to observe Earth from their own solar system from a distance of, say, 10 to 40 light years, they could not resolve the surface directly. Earth would appear as a point of light blended with the overwhelming glare of the sun. But with sufficiently sensitive instruments, they could measure the spectral signature of that reflected light and notice something unusual, a specific absorption feature in the near-infrared, around 750 nanometers wavelength, where the reflectivity of vegetation jumps dramatically and sharply, an effect called the red edge, because it occurs just at the edge between red visible light and the infrared. This red edge is a biosignature. It is produced by chlorophyll's absorption properties. Below 750 nanometers, chlorophyll absorbs and the reflectance is low. Above 750 nanometers, the cell structure of leaves reflects strongly and the reflectance is high. The sharp transition at that specific wavelength is a chemical fingerprint that, as far as we know, requires photosynthesizing organisms to produce. In other words, Earth announces its green biosphere to the universe not in visible green wavelengths, but in a specific near-infrared spectral feature that only makes sense if you know what chlorophyll is and what it does. Any sufficiently advanced telescope pointed at Earth from another star system and sensitive to the right wavelengths would detect the red edge, would see the signature of a planet whose surface chemistry has been reworked by a photosynthetic biosphere, and would understand that something alive is there. The green of Earth is not just a color, it is a signal. It is a flag planted on the surface of a planet by 400 million years of biological colonization, visible across light years to anyone who learns the right spectral language to read it. This is where the entire journey we have taken tonight arrives at something larger than any individual planet's color story. Throughout this exploration, we have been learning a language, the language of planetary color. We have been learning that Mercury's gray reads as no atmosphere, no filter, bare mineral. That Venus's golden orange reads as dense sulfuric acid clouds, catastrophic greenhouse, no surface visible. That Mars's red reads as iron oxide, a planet that lost its water and its air. That Saturn's amber reads as photochemical products staining ammonia clouds, phosphorus, and chemistry meeting sunlight at the cloud tops. That Neptune's blue reads as methane absorbing red light, an active atmosphere keeping the haze thin. That GJ 504b's magenta reads as birth heat, thermal emission of a world that has not yet had time to cool. That PSR J 1719-1438b's colorlessness reads as stripped to the core, crystallized, a former star wearing nothing but its densest chemistry. That 55 Cancre's white-orange incandescence reads as lava ocean breathing volcanic gas, a world rebuilding its atmosphere from the inside. And now, Earth's green reads as life, running continuously for hundreds of millions of years, reworking the surface chemistry of an entire planet, visible from space. Each of those sentences is a translation. And the translation is only possible because we have now learned planet by planet, molecule by molecule, process by process, what the dictionary of planetary color contains. The dictionary entries are not words. They are molecules and temperatures and pressures and geological histories. But they are as precise as any written language, and once you know them, every image of a planet becomes a text. The question that this language now places before us is the one the entire documentary has been pointing toward without stating directly. Can we read the biospheres of other worlds the same way we can read the biosphere of Earth? Can we detect chlorophyll's spectral signature or something functionally equivalent around other stars? The answer, as of 2024 and 2025 is that we are beginning to develop the tools to try. The James Webb Space Telescope, which launched in December 2021 and began science operations in 2022, is the most powerful infrared observatory ever placed in space. Its primary capability for exoplanet science lies in transmission spectroscopy, measuring the spectrum of starlight filtered through an exoplanet's atmosphere during a transit, and looking for the absorption signatures of specific molecules. JWST has already detected carbon dioxide, carbon monoxide, water vapor, sulfur dioxide, and methane in the atmospheres of exoplanets ranging from hot gas giants to the rocky super-Earth 55 Cancri e. It has detected the secondary atmosphere of 55 Cancri e, as we described. It is actively observing TRAPPIST-1 system planets, a set of 7 roughly Earth-sized worlds, orbiting a red dwarf star approximately 40 light-years away, searching for any sign of atmospheric molecules. As of 2025, no biosignature molecule has been definitively detected on any exoplanet. The search is ongoing and has not yet succeeded. But the key point is that it is now technically possible to have this conversation in science rather than only in speculation. JWST can, in principle, detect certain atmospheric gases whose presence would be consistent with biological processes, oxygen, ozone, and methane in combination, for example. Since this combination is thermodynamically unstable in the absence of biology, and its long-term coexistence requires continuous replenishment by living organisms, it can also potentially detect the red edge spectral feature of vegetation if the right telescope and the right target and the right observing geometry are available. The technology is not yet quite powerful enough for Earth twin targets around Sun-like stars. Those require the next generation of space telescopes, including proposed future missions with larger apertures and better starlight suppression. But the methodology is established. The language is understood. The question is whether we are pointed at the right words. Future observatories planned for the next 1 to 3 decades include the Habitable Worlds Observatory, a concept under study by NASA, and the Large Interferometer for Exoplanets, or LIFE, proposed by a European research consortium. These missions are specifically designed to detect biosignatures on rocky exoplanets around nearby stars. Their science cases are built around the spectral language of planetary color, the specific wavelength features that indicate specific molecules, that indicate specific processes, that indicate potentially living chemistry. They are built, in essence, on the same principle that makes Mars red and Neptune blue and Earth green. They are built on the understanding that a world's color, its spectral signature, is its biography, and that biology leaves a specific and detectable mark in that biography. There is a particular concept that encapsulates what we are looking for, and it is worth naming clearly. When astronomers and astrobiologists talk about biosignatures, they are talking about features in a planet's observable properties that cannot be easily explained without invoking biological processes. The red edge of Earth, the sharp increase in reflectance at 750 nanometers wavelength, is a biosignature because no known geological or atmospheric process produces it. Only photosynthesis produces it. The simultaneous presence of oxygen and methane in an atmosphere is a biosignature because these two gases react chemically and destroy each other. So, finding both together in a planet's atmosphere requires explaining why they are both being continuously replenished, and biology is the most plausible explanation. Dimethyl sulfide, a compound produced by marine algae, is a proposed atmospheric biosignature because no abiotic process generates it efficiently. None of these biosignatures are proof of life. They are evidence that would need to be weighed and evaluated and scrutinized with extreme care before any conclusion could be drawn. The history of exoplanet science is dotted with exciting detections that turned out to be instrumental artifacts or misidentified compounds or mistaken spectral assignments. In 2023, a team reported a tentative detection of dimethyl sulfide in the atmosphere of the exoplanet K2-18b, a sub-Neptune world approximately 120 light-years away, using JWST data. The result was described as a hint, explicitly not a confirmation, with the researchers noting that more observations and more careful analysis were needed. The result remains unconfirmed as of 2025. But the fact that we are in a position to have this conversation at all, to be tentatively detecting molecules in the atmospheres of worlds more than 100 light-years away, to be arguing over whether a particular spectral feature represents biology or chemistry, to be designing future missions whose primary scientific goal is to find the spectral fingerprint of life on another planet, represents an extraordinary convergence of the entire scientific project we have been tracing tonight. We started in the gray of Mercury. We walked through sulfuric acid clouds and iron oxide plains and ammonia crystal hazes and methane-absorbing ice layers and photochemical chromophores and atmospheric dynamics. We descended into the diamond rain of ice giant interiors and ascended into the birth heat of a magenta newborn world. We examined the crystalline corpse of a devoured star and the volcanic breath of a world rebuilding its own atmosphere. We came home to the green of Earth and learned to read it as a biological signature visible from space. And now we arrive at the end of the language lesson, which is really the beginning of the most important sentence ever to be attempted in science. The sentence that would begin with a spectral measurement of some distant rocky world and end with the words, "There is life there too." We have not finished that sentence. We have not even confirmed we have the right grammar for it yet. The first few words are still being assembled, letter by letter, molecule by molecule, photon by photon, through the instruments of the most sophisticated observatories human civilization has ever built. But the grammar, the knowledge, that color is chemistry, that chemistry is process, that process records history, and that biology is a specific and detectable kind of chemical process, that grammar now exists. We did not have it a century ago. We barely had it 50 years ago. Today, we can read it in the spectrum of a world 41 light-years away and say, this world is a lava ocean. This world is breathing volcanic gas. This world is not dead. Tomorrow, with better instruments pointed at the right worlds, we may be able to say, this world is green. This world is running photosynthesis. This world has done the thing that Earth did, somewhere else, around another star, in another system, and the universe has done it more than once. When that sentence is finally completed, it will be done in the language of color. Not the color of a painting or a sunset, but the color of wavelengths absorbed and reflected by chemistry on a planetary scale, the same language that Mars has been speaking in red for 4 billion years, the same language that Neptune has been speaking in blue for the same duration, the same language that Earth has been speaking in green for 400 million years, while waiting for someone to learn to read it. We have been reading it all along. We simply did not know what we were reading. Tonight, perhaps, we have added a few new words to our vocabulary. The universe is generous with its vocabulary. Every world that orbits every star is a sentence in a language with no final period, written continuously in light across the entirety of space. The only question has ever been whether we are patient enough and curious enough and careful enough to read. And the answer, it turns out, written in the green of our own planet viewed from above, is yes, we are. Sleep now. Gentle traveler, the universe has been writing to us in color all along, and the letters will be there when you wake.